In this video we're going to look at a proof of the Legendre test for weak extremum. Now I've not talked about weak and strong extremum, but we'll go ahead and talk about that in a different video. So let's just accept it for the moment. Now we've seen whenever we looked at the Legendre test, and we stated it in a previous video, that the extremum, if we call it IS, is a maximum if partial squared f by partial y derivative squared is less than 0, and it's a minimum if partial squared f by partial y derivative squared is greater than 0. So we want to show that this is actually the case, and we want to prove this. Now, as we said in a previous video, we're going to end up with two equations. We're going to end up with the second derivative, in effect, second derivative of the functional, and the second derivative is given in this format here, and remember we derived this via the Taylor polynomial. So we've seen that in a previous video, and we've derived that. And we also derived this other equation here, which is the Jacobi accessory equation, which in effect is like the Euler-Lagrange equation but for the second variation. Now we said before that we were able to find out whether the extremum is a maximum or a minimum just by looking at this term here. So this term here, the f11, that's our partial squared f by partial y derivative squared. And it meant that this term here in effect would dominate and determine the sign of this term here would determine whether we actually had a local maximum or a local minimum. So we're going to use this equation here to simplify this. So let's go ahead and we'll do this now. So before we get started in the details, you can roughly see how we're going to go about this. We don't want this term f01 and f00. We really just want to be left with the f11 term within this equation. So we can see how we're going to do that via this accessory equation, because the accessory equation here has got this factor here, so it's got f00 minus d by dx f01. And you can see here we've got f00 and we've got our f01 here. So what we're able to do is we're able to change this equation slightly so that it looks more like the form that we have here. That will allow us then to substitute in this part here. So in effect, if we were to take this minus across to the other side, we would have this term here would equal d by dx f11u derivative. So it means that we'll be able to, if we do the manipulations correctly, we'll be able to replace this section here with a d by dx f11u derivative, and that will ensure that this function here will only have the f11 terms and not the f01 and the f00. So let's go ahead and we'll work through and we'll knock this into the proper shape. Now I think it was Jacobi who first did this derivation, though I'm not 100% sure. I'll have a look up today and I'll mention it in a later video if I find out exactly who did it. So we're going to start off with this term here. We'll just leave this term exactly as it is. So you can see I've got the I2 down here, epsilon squared by 2 factorial integral from a to b, and this term here, eta squared f naught naught, is exactly the same as eta squared f naught naught there. So we've done nothing to that term. But what we're going to do is we'll change this term here. Now we've seen this before. The 2 eta derivative can be written as d by dx of eta squared. And again, we've mentioned that in the previous video. It's implicit differentiation. So if you differentiate this out, we're going to have 2 eta times d eta by dx, which is going to be eta dash. So we'll have 2 eta dash. So we're going to have this here. Now this part here is going to be multiplied by that f01. So I've just rewritten it here. So it's going to be d by dx eta squared of f01. So that's this little part of the equation here. Now what we can do is we can do integration by parts on this. So we would change the sign to a minus sign, the eta squared is going to come out, and the f01 is going to go inside the brackets, inside the differentiation. So it means that this term here can be replaced with minus eta squared d by dx of f01. And I've got that written down here. So that's this term here. Now we can change this term as well, and we've seen this in a previous video where we're using integration by parts, but we're using it, if you like, backwards. So this term here, which is eta 1 squared f11, well, that's the same as saying minus eta d by dx of eta derived of f11. Now we can see that because if we were to do integration by parts on this, then we would just end up back to this here. And you can see that there we would have eta dash f11 would come out, and then we would differentiate the eta with respect to x, which would just give us a eta dash. So we would have a eta dash squared times the f11. So that's this term down here, and of course the minus sign would disappear because we would have the other minus sign from the integration by parts. So we're going to be left then with this equation here. Now let's have a wee look at the Jacobi accessory equation. We said that we can rewrite that, so what we can do is, if we were to take this over to the other side, then we would have our d by dx f11u derivative, and we take the u over to the other side as well, we're going to have our 1 upon u. So we'll have our f00 minus d by dx f01 is equal to this here. So what we can do then is, if you note here, we're going to have our now f00 and we're going to have our d by dx f01. So you can see that we've started to knock this into the form that we want. So if we take out a common factor of the eta, then we'll be left with an eta times this factor here. But this factor here is nothing other than this, which is equal to this here. So it means we can take this here and we can put it into this equation. And of course we can take the 1 upon u out of here and we'll just put it over underneath the eta here. And we can do the same with the second term. And you can see that we've added an extra u in here because this u will cancel with this one here. And then we'll just be left with what we have above here, which is going to be our eta, which is here multiplying the d by dx, and you have your f11, and I've written the eta derivative as d eta by dx. So that's the first part of our derivation. Let's continue and we'll work through, we'll get it finished off. So I've copied the last equation from the previous page to the top here. So we've seen this equation before. Now this little bit here is the last of the calculus in this proof. The rest of it after this point here will just be bulk algebra. So let's have a look at this line here. We go from this line here to this line here. So you can see that the epsilon squared by 2 factorial integral from a to b by dx, that's just the same as above, and so is the eta upon u. Now the only thing that's changed from this line to this line is that I've taken the eta inside the d by dx here. So in this term here we're going to have our eta f11 and we'll have this term here which is our u derivative. So we see we're going to have our eta and we're going to have f11 and the u derivative. And the same here, I've taken the u inside the d by dx here. So that's going to give us the u and we're going to have our eta derivative here and we're going to have it multiplied by f11. So that's the u, eta derivative multiplied by f11. Now you might be wondering, why is it that I'm able to take the eta and the u inside the d by dx here? It's maybe not that wholly obvious that we're able to do that. So what I've done is I've noted down here the basis of a proof of that. So this is in effect the product rule for three terms. So the product rule for three terms, say A, B and C, would be A dash BC plus A B dash C plus AB C dash. Okay, so that's just the product rule for differentiation extended to three terms. Now this in effect is what we have up here, because we've got three terms here. So we've got F11 eta U dash, so that's in effect, you could say, it's kind of like we could say the A, B and the C. And again here, this term here, we've got three terms, and it's the F11 U eta dash. So those three terms again are equivalent to our A, B's and C's. And we're differentiating it. So if we were to work through this here, and we work through in terms of this differentiation, we would end up with three terms for this and three terms for that. So we'd end up with 6 terms. And whenever you gathered all of the like terms together, you'll find out that it's equivalent to having the eta inside this d by dx and the u inside the d by dx, such that this here is the same as what we have above. Now I've worked through a proof of that myself on pen and paper. What I'll do is I'll put it in the appendix if you're unsure, and you can follow that through from this point in the appendix. So that means that we're going to be left with this line here. So now we're going to go from this line here down to this line here, and again this is all just from this point on is going to be bulk algebra. So actually there's another couple of calculus moves before we get on to the algebra here. So let's say we go from this line to this line here, and what we've done is we want to get access to this F11 section here. We don't want it within inside the d by dx, so we can just use integration by parts in order to get this out. So what happens is the positive becomes a minus, so we get a minus here, and we put the eta upon u inside the d by dx, so that's what we've got here, d by dx eta upon u, and we take this term here outside, and we've got the term outside here. So we've done integration by parts in order to get access to this outside the d by dx. So that's what we've got here. Now there's one other thing that we now do. From this line here to this line here, all of this is just the same. The only thing that's changed is a bit at the end. So what we're going to do is the quotient rule for differentiation. So it's d by dx of eta upon u. So by the quotient rule, it's going to be eta derived of u minus eta u derived of all upon u squared. And if you like, you can have a look up the appendix at the back, and I'll have a note there of the quotient rule. So finally, that's all of the calculus, and we are down now on to the final stages, which is just knocking this into the right shape, and it's just a bit of algebra. So all I've done here is taken the u squared out underneath the F11, and I've multiplied out the brackets. So we multiply out the brackets here. I'll leave you to do that by yourself. So you're going to end up with the 1, 2, 3, 4 terms. So that's 1, 2, 3 and the 4 terms. So let's go on with this, and we'll adjust this algebraically to get it in the right format. So we're almost finished now. We just got to work through some algebra. I've copied the last equation from the previous page, and I've put it up at the top here. So we've seen this before. Now what we want to show is that the sign of the left hand side is really just determined by this factor F11. So a neat way of doing that is to try and get everything that is inside the bracket here as a square, because if it's a square, then the value of all this stuff will have to be positive. So we're really wanting to complete the square on all of this. So let's go ahead and we'll see how we're going to do that. We're going to have the minus epsilon squared upon 2 factorial, the integral from a to b of f11 upon u squared. So that's just the same as above. Now what we're going to do is we're going to multiply these out, and we'll gather the like terms. So you can see that this term here is just the same as this term here. So we're going to have our eta u derivative plus eta derivative u. And you can see we've got our eta and we've got our u derivative and we've got our u derivative and our eta there as well. So this term here is just the same as this term. So we're going to have two of these. And then you can see here that this term here is going to be our eta squared u derivative squared. So that's our eta squared u derivative squared there. And finally, so that's that one, that one. The third term here is going to be our u squared eta derivative squared. And that's our u squared eta derivative squared. So this line here is just the same as this line here, just simplified this little section. Now, this line here, all we've done is we've multiplied throughout by the negative term. So the negative is going in here, this has become positive, this has become positive, and this one here has become negative. So that's all that's happened here. So finally, in this line here, you can see that we've taken the u squared inside the bracket. So we take the u squared in, it cancels with that one. So we just get the eta dash squared. We could take the u squared in here, it cancels with one of those u's, and we're left with one u in the bottom. And we'll take the u squared in here, we've got u squared on the bottom. So now this here is in the form that we can use in order to complete the square. So when we complete the square in this here, what we're left with is our eta dash minus eta u dash all upon u. And you can check that for yourself. If you multiply this out, you're just going to be left with this here. So this is just a basic algebra. So finally, we've got the equation here in the right format. Let's go ahead in the last page and we'll summarise what we've got here, and we'll see why having it in this format is really useful and it proves the result that we want to prove. So again, I've rewritten the last equation from the previous page up the top here. So we've got this equation here. And remember, our f11 is given by our partial squared f by partial y derivative squared. Now we're interested in finding the sign of the left hand side, but we can see here that the epsilon squared, well, it's going to be a positive value because of the squared term. The 2 factorial is going to be positive. This part here is going to be positive as well because it's squared. So all of these terms are going to be positive. The only term that's left is the f11. So the only term here that determines whether the left hand side is positive or negative is the f11. So that's really the final part of our jigsaw, and that's the final part of our proof. So we can say then, in recap for this Legendre test, that the first variation must be met. So this is the Euler-Lagrange equation. We said that f11, it doesn't change sign on AB. If it was to change sign on AB, then the value here, IS, is going to change along with the variation in sign. So we don't want f11 changing over that interval AB. Now, the limits of integration are sufficiently small. Again, we've not talked about that, and we'll talk about that in some other video, but we'll just accept that for the moment. Now, there's one extra proviso here that we've seen that wasn't in our Legendre test, and that's this little section here. So we would have to ensure that this value here didn't equal 0. Because this term here, as we said, we want this term to be a positive value. And it will be a positive value as long as this value inside the brackets here is greater than 0, meaning we will actually have a value if it's greater than 0. But if it was actually equal to 0, then it means that this whole term here is going to disappear. So if this whole term here disappears, it means that in effect the second variation would disappear. So in order to find out whether we actually have a positive or negative value, meaning we have a local maximum or minimum, we would have to look at the third variation. But the problem with doing that is when you come on to the third variation, we're going to have an epsilon cubed, and as soon as you have an epsilon cubed, we're going to have an alternating plus and minus. So therefore we would have to then go on to the fourth variation in order to try and work out whether we have a maximum or a minimum, and we don't really want to be getting into that detail. So what we have to do is we have to ensure that this term here doesn't equal 0. So if it doesn't equal 0 and these conditions are met, then we can say that if f11 is less than 0, it would ensure that we have a maximum, and if f11 is greater than 0, it would ensure we have a minimum. So what we're going to do is we're going to continue and we're going to look at the Jacobi test, and that's going to take account of this here, and we're going to have to work in and ensure that this term here indeed doesn't equal 0. So we'll go ahead and do that, and in the process of doing that we're going to introduce a new idea of conjugate points, which has a very nice geometric property. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.